In this video, I will show you how to run a bivariate regression on SPSS Statistics. From the top tab, when you open SPSS, you find and pick Analyze. Under the Analyze box, you find Regression. And then under the Regression box, you find Linear. So you click on Analyze, Regression, and then you click on Linear from that tab. This usually comes as empty boxes by default if you have not run a regression analysis just yet. So you will put your dependent and your independent variables in these two boxes in order to get SPSS to run your regression. Your dependent variable is your y variable and your independent variable is going to be your x variables. Because we're running a bivariate regression right now, we're just going to have one variable for each box. I'm interested in the relationship between customers' perceptions of quality at Starbucks and the customer overall satisfaction with Starbucks. I am going to make the quality overall my x variable and then my overall satisfaction my y variable. From here, I am just going to go ahead and click OK. Here is the output that SPSS gives me when I run a regression analysis. The first table, which reads variables entered and removed, tells me what I entered as my x variables and my y variables. It tells me that I have one x variable, it's quality overall, and then it tells me that I have one y variable, which is overall satisfaction. In the second table, you can find the Pearson's correlation coefficient R and your R squared. As you will recall, the Pearson's correlation coefficient R tells you whether the two variables or the multiple variables you're looking at are positively or negatively correlated. And it also tells you if there is a moderate, weak, or strong relationship between the variables. So Pearson's correlation coefficient R ranges from -1 to 1. And 0.6 indicates a positive relationship because it's a positive sign in front of it. And 0.6 is a pretty moderate relationship between the variables you entered. So we can conclude from Pearson's correlation coefficient R equaling 0.6 that the two variables have a moderate positive relationship. R squared is equal to 0.371. And this says that the variation in y, 37% of the variation in y, can be explained by my x variable. So 37% of the variance of overall satisfaction can be explained by quality perceptions of customers in this case. The third table that you see here is the ANOVA table, and this ANOVA table tells me if the variables are statistically significantly linearly related to each other. So when this sig over here is smaller than 0.05 and statistically significant, then I conclude that the relationship between my x's and my y is statistically significantly linear. There is a linear relationship between overall satisfaction and overall quality in this case. If this sig value is larger than or equal to 0.05, I will fail to reject my null, which is that there's no relationship between my variables, and therefore conclude that there is no statistically significant linear relationship between my two variables. In which case, I mean, they can be not related, or they can just be related in a different manner. They can be exponentially related, they can be, logarithmically related, etc. But there is no relationship that is linear between the two. In this case, because my f value here is statistically significant, I conclude that quality overall and satisfaction are linearly related, statistically significantly linearly related. Lastly, here we have the coefficients, and this is an important part of my output. It's the fourth table as you see it. Here I will actually try to illustrate what this says to you on the right. So in this table you see that my constant is 1.568 and my quality overall is 0.585. And basically this first column gives me the unstandardized B coefficients, and that is basically a part of this equation that I have in any regression. So A is your constant, in which case here it is 1.568, and then B is the slope in this case for your X variable quality overall, and it's 585. So the first two coefficients that you have here give you your y-intercept, A, and the slope of B. And I had all my variables in my questionnaire on a Likert scale of 1 to 5. So keeping that in mind, let me go ahead and draw this relationship between X and Y for you. So my y-intercept equaling 1.568 means that if my X equals 0, then my Y value, which is satisfaction, this was quality. So if the quality perceptions of customers are equal to 0, which is a hypothetical value because my Likert scale ranges from 1 to 5, so it technically starts at 1, but if it's 0, then the y-intercept is intercepted at 1.568, and then for an increase in quality, X, for 1 unit increase in quality, my y is going to increase 0.58. So it's going to be something around 2, right? 1.568 plus 0.585. So it's going to be actually around 2.1. And then it will keep going like that. So it's going to be around 2.1 plus 0.585, 2.7-ish. For when X equals 2, so on and so forth. This is my y-intercept. This is a data point that lies on my line. This is another data point that lies on my line, and then this is another data point that lies on my line. So my line is, this has to lie on it, so I'm sorry for the little crooked points over there, but this is basically a visualization of my regression equation right here. So these coefficients tell you your regression equation, and then from this equation you can also predict any y that you would like for given x's. Then you have the standardized beta coefficient that is basically the standardized version of your slope, and that is 0.609, and this is equal to your Pearson's correlation coefficient, R, correlation coefficient R in this case, because it is bivariate regression and you're looking at the relationship between one x and one y. So as you see, the Pearson's correlation coefficient R here was equal to the standardized beta coefficient that's related to my only x, 609 and 609. And then something that's important here is the t and the sig values that are associated with your constant and your slope variables. So in the cases where the t appears to be non-significant, we will actually trim our equation and not include either the coefficient constant, the y-intercept, or the slope wherever it's not significant, and only include the variables that are significant to have a trimmed equation, to have an equation that only includes statistically significant variables, A's and B's in it. In this case, both of our variables were statistically significant, so our trimmed equation is this whole equation. We don't drop anything from it. They are all statistically significant. Both the 585 and the second row here came out to be statistically significant, and the y-intercept 1.568 came out to be statistically significant because the sig values are less than 0.05 for both our A variable and the B variable. So that's about it for bivariate regression, and I will talk more about multivariate in another video.